Well, hello everyone. It's been quite a while since I've done a video a lecture, and you guys know that I'm going to actually be out of the state for the next few days, so this will have to suffice. We have started projectile motion and just barely started the first few parts of the notes of it, and you guys probably should be turning those first few questions in today. But we're going to be moving on towards projectile motion in 2 dimensions. We've been talking about it to some degree, but we're actually going to be looking at what happens to an object when it flies through the air. A projectile, which is what we call it right here, projectile is anything that flies through the air or is propelled through the air and then is left alone. It simply flies through the air after that under the power of its original velocity and under the influence of gravity. So you might say a baseball is a projectile. Somebody takes a baseball and throws it through the air. Gravity is affecting it. Gravity is pulling it down. We know that baseballs make an arc or a parabola. It's because of gravity, but the horizontal component of it is because of you throwing it in the horizontal direction. So it has an x velocity or an initial x velocity, but to some degree it may also have an initial y velocity, vyi, as well. And that's why it kind of, if you throw it up at an angle, it makes an arc and comes back down. But nothing else is affecting it. An airplane, for example, is not a projectile because it is powered. It flies under its own power. So something that is launched into the air, like maybe say from a catapult or from a baseball player's arm, but then it simply flies under the influence of gravity only. And so we're going to make a few assumptions with this. What that means is, and you'll need to complete this here, air resistance, we'll say, is ignored. We're going to be dealing with ideal situations here. So if you were to throw a baseball in, say, a vacuum, where would it land? Air resistance, we all know, does have effect in everyday life, but for our purposes right now, that's just going to be one extra thing for us to have to deal with. So we're going to ignore air resistance right now. It is minimal, even in real life, but it would throw the answers off slightly from what we would be doing. So our answers are ideal. We're ignoring air resistance. A second assumption is that the acceleration due to gravity, and you know this, is constant downward, and it is a value of 9.81 meters per second squared. That's what we call g. That's the value, or you might say the absolute value of the g, of the pull of gravity. Of course, we sometimes write it like this. Maybe the acceleration, we would say the acceleration of gravity in the y direction. We would probably write it like that is negative 9.81 meters per second squared. Because if we call down negative, then it always pulls in the down y direction. So we would say that the A is negative 9.81 meters per second squared. And the final thing is that Earth's rotation is ignored. You might be saying, well, why? What's the deal with that? Why do we care about the Earth's rotation? Well, real quick, there's something called the Coriolis Effect. And that's what happens when we have a rotating Earth. Let's say we have the Earth right here. That's not a bad circle. And we're looking at it from the top. So this is the North Pole right here. And let's say the Earth is rotating that way. Okay? If you try to throw something in a straight line, or project something, or launch something in a straight line, say from the North Pole down to the equator, since the Earth is rotating, it will actually take a curved path over the Earth because the Earth is moving underneath it. So if the Earth is rotating that way, then the object thrown would actually slightly curve off to the right. We call that the Coriolis Effect, and some people blame baseballs being a home run or not a home run, making inside or outside the home run pole as being because of the Coriolis Effect, the Earth turning because of that. Well, I'm not sure if that and that small of a scale affects it. But the Coriolis effect does affect things like hurricanes and ocean currents. These things that winds want to blow and currents want to blow in a straight line actually do curve because of the Earth moving underneath it. So for our purposes, once again, we're going to idealize our situation. The rotation of the Earth is going to be ignored, so we're not going to worry about the Coriolis effect or air resistance, for that matter. You might say, or friction. So they're going to go away, and our ideal gravity is 9.81 meters per second squared in the negative y direction. So that's the basic premise on which we do projectile motion calculations. So let's take this and let's find some equations then for it.